Friends, many of you had asked me to make a video on singularity. So when I searched for this topic on YouTube, I found a lot of videos about singularity. But there was one thing missing in all those videos. Instead of the actual definition of singularity, those videos were telling us about the consequences of singularity. Meaning, when you reach the singularity of a black hole, what happens to you, what happens to matter, what happens to light, or some hypothetical thoughts like the singularity being a portal to another universe. So this video is generally correct, but to understand it in layman's terms, you can refer to them. But if you ask a physicist about singularity, they definitely won't explain it to you the way it's shown in YouTube videos. So today let's look at the actual definition of singularity. Today we will look at those results where singularity appears in General Relativity. Well, ideally you should have some knowledge of General Relativity to understand this topic, but still, I will try to simplify it a bit and explain it in an easier way. For that, you will need to watch this video with full attention. So, if I talk about General Relativity now, General Relativity tells us about the nature of gravity, what gravity actually is. So the whole idea of General Relativity is, if we define it in one line, that gravity is geometry. In fact, in General Relativity, you are actually studying geometry, and studying geometry isn't all that tough. And if we put it in John Wheeler's words, matter tells spacetime how to curve, and spacetime tells matter how to move. This means that matter tells spacetime how it should curve, and spacetime tells matter how it should move within that curvature. This is the whole idea behind General Relativity. So, to understand singularity, we need to start from the very basics, and in the end, you'll see that we don't even need to define singularity. Singularity will automatically start appearing in our equations on its own. So first of all, in the geometry you've been studying since childhood, what do you do in that? Simply, with the help of geometry, you calculate distances, lengths, angles, areas, volumes, all these things. And to calculate all these quantities, you need coordinates. Coordinates give you the line element. Well, now we'll understand this a bit with an example. First of all, let me tell you about the line element. Actually, the line element is the shortest distance between 2 points on any curve. We represent this by d's. So, to study any kind of geometry, your most basic requirement is the line element. If you want to study our space, you will need the line element of that space. And believe me, you've been studying the line element since childhood. Here, take a detailed look at this fundamental and simple formula. When you study mathematical concepts such as matrices, which are rectangular arrays of numbers, tensors, which are geometric objects that describe linear relationships, and coordinates, which specify positions in space. You get volumes, you get geodesics. That is, by combining line elements and calculus, you can obtain information about everything. But right now, you must be wondering what exactly is this metric tensor? We have heard about coordinates, so for now, I won't define the metric tensor because it's quite a big topic in itself. Try to understand it through an example. So now I'll show you a simple Cartesian coordinate system. In this, we'll try to calculate the line element. So, we know the coordinates are x and y, and its metric tensor is 1, 0, 0, 1. In this case, the value of the line element comes out to be ds squared equals dx squared plus di squared. And by what name do you all know this formula? By the name of the distance formula, and here ds represents the shortest distance between 2 points. So, in any curve, the shortest distance between 2 points is called the line element. And when you combine the line element with calculus, you can find the length, area, and many other quantities. Similarly, in the spherical coordinate system, the metric tensor is like this. What are the coordinates? R, theta, and phi. And when you calculate the line element, it comes out as doctor squared plus r squared d, theta squared plus r squared sine squared theta d, phi squared. Similarly, when you talk about higher dimensional space, like when Einstein combined space and time in his special relativity, the metric tensor looks something like this. In this, the first term is -1 and all the terms on the diagonal are 1. In this, there is one time coordinate and the rest are space coordinates. We denote the time coordinate with a negative sign and the spatial coordinates with a positive sign. You can also do the opposite of this. So for now, its line element comes out to be minus c squared dt squared plus dx squared plus dy squared plus dz squared. This represents the line element in flat spacetime. This type of space is called Minkowski space. So if our universe were flat, then you could define everything using just this formula. But our universe is not flat. Mass brings curvature to its fabric, and when curvature is present, the geometry changes and we have to use general relativity. So now I'll show you Einstein's field equation, which explains how spacetime tells matter how to move and how matter tells spacetime how to curve. G mu nu equals 8 p gt mu nu. So what is g mu nu? r mu nu minus 1 upon 2 g mu nu r. Now, to understand this equation, you need to have knowledge of tensorial algebra, which we don't have right now. So for now, we'll skip these terms. But what is the ultimate aim of this equation? Actually, we need to find the comprehensive and precise solution to this fundamental field equation, which is a mathematical representation of physical laws governing the universe. And the solution, once obtained, will meticulously provide us with a detailed and exhaustive description of various fundamental quantities of space, such as its curvature, its metric, and how these properties evolve over time. So, different. Einstein's equations were solved for a spherical system. This is what we call the Schwarzschild spacetime equation. So, the description of a black hole comes from the solution to this Schwarzschild spacetime equation, which defines spherical geometry. So in Einstein's equation, what you see as g mu nu, ultimately that's what we have to find. So first of all, we will find this. We take a coordinate system. In this case, our coordinate system is spherical coordinates. Now the second thing we need is the metric tensor, so we calculate the metric tensor, and then after that, we see a symbol like this. This is called the Christoffel symbol. The Christoffel symbol is calculated with the help of the metric tensor, and then these Christoffel symbols combine to give us the Ricci tensor, which we call r mu nu. So here the r mu nu term in the Einstein field equation is the Ricci tensor. And when the Ricci tensor is combined, that is reduced, we call it the Ricci scalar, which we denote by r. And what is our metric tensor? G mu nu. And on the right hand side, you can see T mu nu. We call this the stress energy tensor. So in the case of Schwarzschild spacetime, the value of T mu nu is 0. So if the value of T mu nu is 0, it means we are talking about Einstein's vacuum equation. So we only need to solve the equation on the left hand side. And here, in the calculations you see on the screen, we are only solving the equation on the left hand side. And although it looks complicated, but believe me, solving it is actually quite easy. See, first we found the metric tensor gmu nu, then we found the Christoffel symbols, and then with the help of the Christoffel symbols, we found the Ricci tensor, and then we calculated the Ricci scalar, and finally, we combined all these values. And what did we finally get? The ds squared line element. This is what we call the Schwarzschild metric. And once you have this, as I told you at the beginning of the video, you can combine it to find the remaining quantities. So this is actually quite simple. So ultimately, you have found the Schwarzschild metric, that is, you have found ds, you have found the line element, and with its help, you can calculate all the other quantities. Now we will analyze the Schwarzschild metric. So now, since this Schwarzschild metric is the spherically symmetric solution to the Einstein field equations. So if there is any spherical star in our universe, you can describe the spacetime around it using the solution of this Schwarzschild metric. However, this solution is only valid outside the star. Why is that? Because remember, at the beginning, the T mu nu that we took on the right hand side, in the case of Schwarzschild, we assumed T mu nu to be 0, so this is its vacuum solution. The solution inside the star will be different. However, it is crucial to acknowledge and understand that despite initial appearances and common perceptions, the underlying circumstances and prevailing conditions present a considerably different and more complex perspective than what might be immediately obvious. The matrix component you're seeing, we'll call that GO0, and the component next to Dr. squared, we'll call that GRR. Now suppose here where you see 1 minus 2 gm upon r, what does r represent here? It's your radius. So if you put in different values for r, you'll get solutions corresponding to different radii. Now suppose we set r equal to 2 gm or set 2 gm equal to RISS, then your GO0 component becomes 1 minus RISS upon r, and the GARR component becomes the inverse of 1 minus RISS upon r. Now see, there are two regions here that will create problems for you. The very first reason is if the value of r becomes equal to RISS, then in this case the GRR component will approach infinity. And the second problem is if the value of r becomes 0, then in that case the GO0 component will approach infinity. This means that if the value of r becomes equal to RISS, or if the value of r becomes equal to 0, then in that case your answer will be infinite, it will be undefined. That is, you can clearly see in this equation that these two regions will create problems for you. When your r becomes equal to 2 gm, or when your r becomes 0, that is, at the center, then whenever your metric components blow up to infinity, we call that a singularity. Now, singularity means that we cannot define or describe the geometry of spacetime in that region. We simply do not have any solution at that point. It's an undefined solution because if your metric components become undefined, it means you won't be able to calculate the line element. And if you can't calculate the line element, then you can't calculate the length, area, or distance in that region of space either. You won't be able to calculate anything at all. This is what we call a singularity point. But look, there are actually two types of singularities. The first is called a coordinate singularity. Actually, this type of singularity occurs when you choose a wrong or bad coordinate system. It means whenever you choose a bad coordinate system, you encounter a coordinate singularity. You can remove this type of singularity by modifying your equation. For example, look at this example. ds squared equals do squared over u to the power of 4 plus d theta squared over u squared. Now, when you put the value of u as 0, you'll see that the value of ds squared becomes infinite, meaning you'll get an undefined solution. But this is not a real singularity. If we change the coordinates, that is, if we put u as 1 upon r, then this singularity will be removed. So the geometry that I just showed you becomes ds squared equals doctor squared plus r squared d theta squared, which means it becomes a two-dimensional polar geometry. So now, even if you put 0, you'll get the answer as 0, but it won't be undefined. So the singularity that you were seeing earlier was actually due to your bad coordinate system. The second type of singularity is called curvature singularity, and this type of singularity cannot be removed by changing the coordinates. These are the points where invariant quantities approach infinity. What are invariant quantities? For example, space-time curvature. So if the space-time curvature itself approaches infinity, we call that a curvature singularity. So here, in the Schwarzschild metric, you find both types of singularities. Both coordinate singularity and curvature singularity. You encounter a coordinate singularity when your radius is equal to r's, that is, when the value of r is 2gm. We also call r equals 2gm the Schwarzschild radius. We can also call this the event horizon. So according to this equation, when you reach the Schwarzschild radius, that is, when you reach the event horizon, the singularity you encounter is called a coordinate singularity. But this singularity can be removed by using different coordinates, such as by using Eddington-Finkelstein coordinates. Anyway, we won't go into that right now, but after changing the coordinates, you get a solution like this. In this case, you can see that the coordinate singularity has been removed, meaning that when r equals rs, you won't encounter a singularity. The answer will not be undefined. That is, in this way, your coordinate singularity gets removed, but you will still see that the curvature singularity remains. That means when you put the radius to 0, it means you are exactly at the center of the black hole. R is equal to 0, then you will get the solution defined. So, in the case of a black hole, you have removed the coordinate singularity, but the curvature singularity still remains. So, in the case of a black hole, you will always encounter a curvature singularity, and in that case, we cannot define the solution, and it was this curvature singularity that troubled our scientists for many years. In fact, for a time, there were doubts about the Schwarzschild solution. However, the Schwarzschild solution is still useful for investigating curvature around a black hole. Similarly, there is another set of coordinates called Kruskal coordinates, which you can use to remove coordinate singularity. And by using these coordinates, you also get a bit of a description of a wormhole, that if a black hole exists, then a wormhole must also exist. We won't go into this right now, but yes, ultimately, if we can find a spacetime metric that doesn't allow any curvature singularity at the center of a black hole, then you'll also be able to describe the physics happening at the center of a black hole. So what is your ultimate aim? You have to prevent the value of the metric tensor at r equals 0 from becoming infinity. Because whenever you allow the mathematical operation of division by 0 to occur within any of your established theories, fundamental equations, or logical frameworks, you inevitably arrive at an undefined answer. This undefined result is not merely a lack of a specific number, but rather a concept that often leads to an infinite value, which signifies a quantity without bound or limit, thereby breaking the consistency and predictability of the theoretical system. So does this mean we need a better theory? So in summary, we looked at two types of singularities. First, the one that exists at the Schwarzschild radius of a black hole, and second, the one that exists at the center of the black hole. The first type of singularity can be removed by changing the coordinates of the Schwarzschild solution, but the singularity at the center cannot be removed. And why does this occur? Because we allowed division by 0, so you got an undefined answer. Whenever the metric components blow up to infinity, you'll start seeing singularities in general relativity. At that point, you can't define any quantities. You can't calculate length, you can't calculate distance, you can't calculate volume, nor can you define geodesics. It means there is simply no mathematical solution there. All of this is what mathematics tells us. We haven't actually gone near black holes to see for ourselves. We define singularities solely on the basis of results from mathematical theory. We observe them in our theories. In fact, in any physical theory, if your solution blows up to infinity, you will encounter a singularity, and the job of a physicist is precisely to remove these singularities. Only then will you have a perfect theory. So does this mean that our theory of black holes is still incomplete? Well, be sure to let me know your thoughts in the comments section. So guys, that's all for today's video. Well, this might be a bit difficult for you to understand because here we've discussed things in terms of general relativity, and I think very few of you have studied general relativity mathematically. But from this, you can get a bit of an idea about how singularities arise. So that's absolutely everything for today's insightful video. We will definitely meet again in the very next exciting video. Until that wonderful time, please do remember to enthusiastically like this video, generously share it with all your cherished friends, and if you haven't already subscribed to our amazing channel yet, please do make sure to subscribe promptly so you absolutely don't miss any of our incredibly valuable upcoming videos or important updates.